Ladies and gentlemen, welcome to Introduction to Waves. Our essential question is, what are the characteristics of mechanical and electromagnetic waves? As you make your way through this PowerPoint, please fill in the waves graphic organizer that looks like what you see on the screen. So what are waves? What's the definition of a wave? A wave is a rhythmic disturbance that carries energy without carrying matter. I'm sorry that my dog is growling. I'm not sure I'm going to be able to keep her from doing that, but I'll try to keep her quiet. A wave is a rhythmic disturbance that carries energy without carrying matter. What kind of? There are two kinds of waves. There are mechanical waves and there are electromagnetic waves. um, Mechanical waves need a medium to transfer energy. So mechanical waves have to pass through something. They have to be able to move through something. I have the television on, and she sees things on television, and she's trying to get them. So maybe if I turn the television off. So a medium is the substance through which the wave moves. So the substance could be air, water, particles like sand, the ground, like in an earthquake, strings, any kind of solids, liquids, or gases. So a medium is any kind of substance. Electromagnetic waves, on the other hand, don't need matter to transfer energy. So as we said last time, electromagnetic waves can move through the vacuum of space. And since electromagnetic waves do not need a medium, then they can go through things like air, water, glass. Electromagnetic waves, remember, an electromagnetic wave is by definition a light wave. So here's some more examples of mechanical waves. And those are waves that need a medium to transfer energy. So sound waves, ocean waves, ripples through water, the waves of people at a sporting event when people put their hands up, and do the wave. So here are some examples. These are some pictures of what mechanical waves look like. Notice right here, this is a sound wave. So we're going to talk a little bit about how sound wave is a little bit different than these other two. But these are all mechanical waves because they have to move through a medium. So if you think about this, think a little bit about some of the things we just saw about mechanical waves. I don't know that you need to really talk to another person about it, but just kind of consider which type of mechanical wave do you think transfers the most energy in the example like this? All right, so there's a couple kinds of transverse waves. There's a transverse mechanical wave, and in a transverse mechanical wave, the pulse of energy is perpendicular to the direction that the wave moves. So the matter in the medium goes up and down in a transverse wave, and the wave itself goes side to side. We're going to take some notes about that on the sheet that looks like this, and we're going to start by talking about that transverse wave, the top half of the page. So, as I said before, in a transverse wave, the energy pulse is perpendicular to the direction of the wave motion. The very top of a wave is called the wave crest. It's the highest point on the wave. And the lowest point on the wave is called the trough. And that's the kind of valley area between two crests. The wavelength is the distance from the same point on the wave to the same point on the wave. So the best way to think of that is from crest to crest or trough to trough. It's the wavelength. Amplitude is the height of the wave from its rest position. It says here that it's the distance from the undisturbed level to the crest or trough. And these pictures show that. So this is amplitude. So from this rest position to the crest, or from the rest position to the trough. Another way to think of it is if you look at the whole wave, the amplitude is half of this total height. An ocean wave is a mechanical transverse wave, and it includes all the pieces we just talked about. It has a crest, a trough, and its wavelength goes from crest to crest, and it has an amplitude. However, the wave height here is not the amplitude. The amplitude would be half of that wave height. Okay, so here's another set of pictures that kind of reinforce the idea of the parts of a mechanical transverse wave. Okay, so the next kind of wave is called a longitudinal wave. Here it's also described as a compressional wave, but it's most often called a longitudinal wave. And a longitudinal wave is a wave where the pulse is in the same direction as the wave motion. So the mechanical wave has a pulse that moves this way, and the wave motion also moves that way. So one of the ways you can think about a compression wave or a longitudinal wave is that it's kind of like some stretching and squishing. Because if you notice here, this shows that there's bunches of particles separated by less densely packed particles. So that's the way compression waves work. So you're going to use the bottom half of this page to make some notes about that. In a longitudinal wave, the compression wave is the part where the particles get crowded together. So this is the compression part of the wave. Then in a longitudinal wave where the particles spread out, that's called rarefaction. So this is the part of the wave that's called rarefaction. This is the compression part of the wave. This is the rarefaction part of the wave. Again, these are longitudinal waves. Also, there's a wavelength for a compression wave or a longitudinal wave, and it's the distance from compression to compression or rarefaction to rarefaction. This is kind of an example of how sound waves work. Sound waves are longitudinal waves. Sorry. So if these are the molecules that make up the air, then they're distributed pretty uniformly. And then whenever there's a sound that comes off the top of this drum, then the molecules kind of bunch together. And then after that pulse is over, that bunched up area of molecules moves through the air, and it's followed by an area where there's not as much concentration. That may be a little hard to see in these images, but it's kind of the general description of how sound waves work. And remember, a sound wave is a longitudinal wave. Okay, so in review, electromagnetic waves are waves that do not need any kind of a medium to transfer energy. And they're light waves, like TV and radio waves, X-rays, microwaves, lasers, energy from the sun, visible light. And electromagnetic waves are transverse waves. The electromagnetic spectrum we looked at last time, and it tells us a bit about the range of wavelengths and frequencies of electromagnetic waves. However, all of the waves on the electromagnetic wave spectrum are all light waves, and they all travel at the speed of light. Okay, if we look at this, there's a couple of questions here. Which has the longest wavelength according to this graphic? A microwave, a gamma wave, a radio wave, or an ultraviolet light wave? The wavelengths are given up here across the top, and this is 10 to the third. This is 10 to the minus 12. So the longest wavelength is going to be down here. So in the list that's provided, the longest wavelength is a radio wave. Some radio waves can actually have wavelengths that are several miles across, particularly radio waves that transmit through space. And the next question, number 2, is which one has the highest frequency. Um, Here's the frequency line. So here's 10 to the fourth, excuse me, 10 to the sixth, and this is 10 to the 20th. So this is a very, very high number. So the higher frequency waves are the one toward this end. So a gamma wave would be the wave with the highest frequency in this list. Okay, let's do this list. Let's compare these kinds of waves. So compare a sound wave, an ocean wave, a wave on a rope, and a stadium wave. Which one of these does not belong, and why doesn't it belong? See if you can make your choice. I pick a sound wave because a sound wave is a longitudinal wave, and the rest of them are not. The rest of those waves are transverse waves. So for number 2, a microwave, an X-ray, a laser, and a sound wave. Which one of those does not belong? Well, 3 of those are on the electromagnetic spectrum, so they are light waves. One of them is not. A sound wave is not an electromagnetic wave. On number 3, a radiation wave, radio signal, a light wave, and an earthquake. Well, in this case, an earthquake does not belong because radiation, a radio signal, and light waves, those are all electromagnetic waves. And an earthquake is the only one in the list for number 3 that's not an electromagnetic wave. And for the last one, a sound wave, a ripple in the water, a guitar string, and a TV signal. Well, number 4 is really just a repeat of number 1. A sound wave is a longitudinal wave, and so it is unlike the other ones. All right, thank you very much. Do a good job.